Next chapter, Organic Chemistry 1. Now, organic chemistry is the chemistry of compounds of carbon. Organic compounds are a large class of chemical compounds in which one or more atoms of carbon are covalently bonded to atoms of other elements, commonly hydrogen, oxygen, and nitrogen. Carbon has an electron configuration of 2 to 4, meaning it has 4 electrons in the outer shell. Carbon can gain 4 extra electrons to form an anion C4 negative, or lose 4 electrons to form a cation C4 plus. However, more often than not, neither of these happens. Carbon completes its octet configuration by covalently bonding with other atoms. For instance, in methane molecule, carbon forms 4 covalent bonds with 4 hydrogen atoms. Carbon can also form covalent bonds with other carbon atoms in a process called catenation. This results in molecules with long chains of carbon. The catenation property is because carbon has a very small size with only 2 energy shells, which helps the nucleus to hold the bond strongly and hence making the overall structure very stable. Organic compounds are classified based on their functional groups, which give the compounds their physical and chemical properties. In this chapter, we look at one group of organic compounds called hydrocarbons. Hydrocarbons are compounds of hydrogen and carbon only. The carbon atoms join together to form the framework of the compound, and the hydrogen atoms attached to this framework in different configurations. Hydrocarbons are the principal constituents of petroleum and natural gas, serving as fuels and lubricants, as well as raw materials for products of plastics, fibers, rubbers, solvents, explosives, and industrial chemicals. Hydrocarbons are classified into 3 groups according to the type of the carbon-carbon bonds present. These are alkanes, alkenes, and alkynes. Alkanes are hydrocarbons in which all the carbon-carbon bonds are single. Each carbon atom in alkanes therefore exercises its maximum covalency of 4. In other words, each carbon atom is bonded to 4 other atoms covalently. All alkanes have molecular formula that satisfies the general formula CnH2n plus 2, where n is an integer and it's never 0. The simplest alkane has 1 carbon atom. From the general formula, we shall have a molecular formula CH4. The molecular formula only shows the type and number of atoms in a compound. A structural formula, on the other hand, shows the bonding between the atoms in a compound. And so, this is the structure of methane. A carbon atom forming 4 covalent bonds with 4 hydrogen atoms, seemingly at right angles. However, in reality, the 4 hydrogen atoms take up positions that are as far away from each other as possible. So they form this kind of a tetrahedral arrangement. But because it's virtually impossible to represent these kind of structures on a paper, we will be content with the 2-dimensional formation. The second alkane has 2 carbon atoms. From the general formula, we shall have 6 hydrogen atoms. This is called ethane. In the structure of ethane, we find that each carbon is bonded to 3 hydrogen atoms and then to each other. Remember that a covalent bond is simply a shared pair of electrons. And so if you consider each carbon atom, you will see that it has formed 4 covalent bonds with 4 other atoms, so the valency of carbon is satisfied. The next alkane has 3 carbon atoms, and so it will have 8 hydrogen atoms. This is called propane. To draw the structure, we first draw the 3 carbons bonded covalently in a straight line. The first and the last carbons each has formed one covalent bond. The middle one has formed 2 bonds already, but each carbon must form 4 covalent bonds. So the first and the last carbons each attach to 3 hydrogen atoms. Their valency is satisfied. The middle carbon needs 2 extra bonds, so 2 hydrogen atoms attach there. The fourth alkene has 4 carbon atoms and 8 hydrogen atoms. It's called butane. Drawing its structure, the carbons at the ends attach to 3 hydrogen atoms. The middle ones attach to 2 hydrogen atoms each. Next is 5 carbons, meaning we shall have 12 hydrogens. This is pentane. The structure follows the same pattern. 3 hydrogen atoms for the carbons at the ends and 2 hydrogen atoms for the inner carbons. Next we shall have hexane, then heptane, octane, and nonane with 9 carbons and 20 hydrogen atoms. Next item, we'll look at condensed structural formulae. Now obviously, writing this open structural formula is not just tedious, it is also time consuming, not to mention it takes a hell lot of space. We can condense these structures by removing the bonds and only showing the type and number of atoms in the molecule. Consider the structure of ethane. We see that each carbon is bonded to 3 hydrogen atoms and then to each other. We can remove the bonds and we write CH3, CH3. Look at pentane. The first carbon is bonded to 3 hydrogen atoms, so we have CH3. The next one is bonded to 2 hydrogen atoms, so we have CH2. Another CH2, again another CH2, and lastly CH3. We can even condense this structural formula further. Looking at it, we have 3 CH2 groups, and instead of writing all of them, why not write one, put it in a bracket, and indicate that there were 3 of them? That's better. Look at heptane. We shall have CH3, CH2, 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 and CH3. We condense this further, we have 5 CH2 groups, and so we shall have CH3, 5 CH2 groups, and then CH3. Now, if you keenly look at the structures of these compounds, you will realize that each differ from the next one by a single CH2 group. Such group, in which successive members differ by a specific number and type of atoms, is called a homologous series. Members of a homologous series have almost similar chemical properties and show gradual variations in physical properties. For example, boiling points and densities will increase with increasing molecular mass. Next, alkyl groups. Alkyls are groups of hydrocarbons in which one carbon atom has an unpaired electron. This means that the group can form a covalent bond with another molecule. Alkyls are obtained from alkenes by way of losing one hydrogen atom. Consider methane. If methane loses one hydrogen atom, it becomes an alkyl called methyl. We just replace the N in alkanes with -yl. In condensed form, we write it as CH3 with a dash indicating an unpaired electron of carbon. If we had ethane, we remove one hydrogen, it becomes ethyl, and so on and so on. Next, branched alkanes and isomerism. Now, the structures of alkanes that we have seen so far consist of linear or continuous chains of carbon. They are also called continuous chain alkanes. In certain other cases, however, alkyl groups may replace one of the hydrogens attached to the middle carbons. Consider the structure of propane. This is a continuous chain. Suppose a methyl group replaces one hydrogen here. Then we shall have a branch. This structure is said to be a branched alkane. In condensed form, we write it like this. We can even have another methyl group replacing this other hydrogen atom. So we have two branches. In condensed form, we shall have this structure. In this case, the hydrogens that were replaced were those attached to the middle carbon. Here is something interesting. Could a methyl group replace a hydrogen attached to either of the end carbons? Yes, it can. But does that mean it's a branched alkane? Absolutely not. Why? Let's look at propane again. Suppose we say that a methyl group replaces this hydrogen. This is the structure that we shall have. Is this a branched alkane? Not at all. If you were to write its condensed form, we shall have this structure. When we talk about continuous chain, it does not necessarily mean horizontal or straight. This compound is the same as this. You can even write it like this, or even this. I have just put those bonds for you to see the formation of that structure. Now, the chain is continuous even though it is not straight. This molecule is a butane and not a branched alkane. In simple, for a single alkyl group to qualify as a branch, it must replace a hydrogen attached to one of the inner carbons and not any of the carbons at the ends. The branches need not be alkyl groups. You can have halogens like bromine, chlorine, iodine, fluorine, and others. The most important thing is to maintain the valency of carbon. Now the question is, what are the names of these branched alkanes? We look at the nomenclature of branched alkanes. Let's use the condensed structures to name the branched alkanes. Consider this structure. This is a branched alkane. Branched alkanes have two types of chains: the parent or the root chain and the branch chain. The parent chain is the continuous chain, but remember, continuous does not necessarily mean straight. So in this compound, we can think of the continuous chain as this horizontal section, in which case this carbon will have two branches of methyl groups. We can also think of this as the continuous chain. In this case too, this same carbon will have two methyl branches. Lastly, you can think of this as the continuous chain. And again, the same carbon has two methyl branches. For simplicity, let's use the horizontal case. Naming of branched alkanes is governed by a set of rules. Number 1, we determine the longest continuous chain of carbon atoms, and this will give the parent name. In this case, the continuous chain has 5 carbons, and so the parent name is pentane. Number 2, we number the carbon atoms in the longest continuous chain. The numbering can be done either from right to left or left to right. However, in numbering the carbons, we ensure that the carbon numbers bearing the branches make the lowest possible combination. For instance, in this case, if we number our chain from left to right, bromine will be on carbon number 3 and the methyl groups will be on carbon number 4. 3 plus 4 is 7. On the other hand, if we number from right to left, the methyl branches will be on carbon number 2 and bromine will be on carbon number 3. 2 plus 3 is 5. So this is the correct numbering because it gives the lowest combination of numbers. Number 3, we identify the substituent groups or the branches and we write them alongside their positions on the continuous chain. If more than one similar groups are present, we use the prefixes di for 2, tri for 3, and tetra for 4. So in this case, we have 2 methyl groups, both attached to the carbon number 2. So we shall have 2,2-dimethyl. And then we have bromine attached to carbon number 3. So we shall have 3-bromo. Number 4, we now combine them alphabetically, separating them with a hyphen and add the parent name at the end. So we shall have the name of this compound as 3-bromo 2,2-dimethyl pentane. Now let's look at isomerism in alkanes. Isomerism is a feature whereby compounds have the same molecular formula but different structural formulae. Consider the structure of butane. The condensed structure is this. It is called N-normal butane or N-butane in the common language. The molecular formula is C4H10. It says that there are 4 carbons and 10 hydrogen atoms in this compound. Now, suppose this methyl group breaks off from the chain and swaps position with this hydrogen atom. You see, now we have a branched alkane. Its condensed structural formula will be this. Following the rules of naming branched alkanes, this structure is called 2-methylpropane in the IUPAC system. In common language, it's called an isobutane. Here's the interesting thing. If you count the number of carbons on the isobutane structure, it is 4, and hydrogen atoms are 10. So the molecular formula of 2-methylpropane is C4H10, the same as that of normal butane. This is called isomerism, and the two structures, N-butane and 2-methylpropane, are called the isomers of butane. Generally, butane has 2 isomers, N-butane and isobutane. Let's look at pentane. With pentane, there are 3 possible isomers. When all the carbon atoms are aligned in a linear fashion, the isomer is called N-pentane. Its IUPAC name is pentane. This is the first isomer. The molecular formula is C5H12. When a methyl group shifts and attaches itself to the second or third carbon, it forms a 2-methylbutane. The common name is isopentane. If you count the number of carbon and hydrogen atoms, the molecular formula will still be C5H12. For the third isomer, one more methyl group breaks and attaches itself to the same carbon, forming a double-branched alkane called 2,2-dimethylpropane. Its common name is neopentane. Counting the number of carbon and hydrogen atoms, they are still 5 and 12 respectively, and so the molecular formula is still C5H12. So pentane, 2-methylbutane, and 2,2-dimethylpropane are the three isomers of pentane. Basically, in isomerism, what we do is relocate one terminal methyl group to attach to one of the inner carbons to form branches. As long as the valency of carbon is maintained, the molecular formula doesn't change. The more the number of carbon atoms in a compound, the more the number of isomers. We look at one more, hexane. The molecular formula is C6H14. First isomer, when all the 6 carbons are joined in a linear fashion, we shall have our first isomer, the normal hexane. Second isomer, if this terminal methyl group breaks and attaches to the second carbon, we shall have another isomer, 2-methylpentane. The condensed structure is this one. If it attaches to the third carbon, we shall have the third isomer, 3-methylpentane. The condensed structural formula is this one. What if it attaches to the fourth carbon? Would we have 4-methylpentane? No. In this structure, we would number the carbon atoms from right to left. So the branch is now on carbon number 2, and the structure will be 2-methylpentane, and we already have that. From this structure, 2-methylpentane, we can form another isomer. If this terminal methyl group detaches and shifts to the second carbon, we shall have another isomer, 2,2-dimethylbutane. Again, from this structure, one methyl branch can move to carbon number 3, and we shall have 2,3-dimethylbutane. What if both branches shift to carbon number 3? The structure becomes 2,2-dimethylbutane because now we will number the carbons from right to left to give the lowest number for the branches, and we already have that structure. So hexane has 5 isomers: N-hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. All have the same molecular formula, C6H14, but differ in the structural formula. Notice that when isomers form, the parent name changes to a lower one to ensure that the molecular formula remains the same. So much for structures. We now look at the occurrence of alkanes. Alkanes occur naturally in petroleum and in natural gas. Petroleum is mined from oil fields as crude oil. It's a complex mixture of different substances, mainly hydrocarbons, with alkanes comprising about 90%. Natural gas occurs as gas above crude oil in oil fields or dissolved in crude oil. It also occurs as gas deposits in gas fields. Its major component is methane, but it also contains small quantities of ethane, propane, and butane. In its natural form, crude oil is not of much use. It has to be separated into various useful components through refining. The refining of crude oil is done through a process called fractional distillation. For this, a fractional distillation column, also called a fractionating tower, is used. After removal of suspended solids and gases, crude oil is heated to a temperature of above 400 Celsius degrees. The hot oil is fed at the bottom of the tower. Components with the highest boiling points remain at the bottom of the liquid and are removed. These include asphalt and tar. The other components vaporize and rise up the tower. The vapors pass through a series of bubble caps and trays that cool them as they rise above the tower. Components of the vapor with higher boiling points, that is lubricating oil, heating oil and diesel oil, condense in liquids at the middle of the tower. Here, they are trapped over the trays and removed. Kerosene and gasoline, which have lower boiling points, condense into liquids near the top of the tower and are removed. Natural gas, which is the component with the lowest boiling point, is removed as a gas at the top of the tower. Next, cracking of hydrocarbons. Now, the short chain alkanes from 1 carbon to 12 carbons are more in demand than the long chain alkanes. Long chain alkanes can be broken down to short small alkanes by a method called cracking. In thermal cracking, a refined crude oil fraction containing long chains of alkanes is heated to a temperature of 700 Celsius degrees. At this temperature, some of the carbon-carbon bonds break. This results in a mixture of short chain alkanes as well as alkenes. Laboratory preparation of alkanes. Methane is the smallest alkane and it's also called marsh gas. The apparatus set up for its preparation are shown here. A mixture of sodium ethanoate and soda lime are put in a boiling tube. The mixture is heated, first gently and then strongly. Methane gas is liberated and collected over water. Methane is a colorless gas with a distinct smell. It's insoluble in water and less dense than air. Chemical properties. Combustion. Methane burns with a blue non-sooty flame, producing carbon dioxide, vapor, and a large amount of heat. Substitution reactions. Alkanes react with halogens except iodine in the presence of sunlight to give a variety of products. In these reactions, UV rays from sunlight provides the energy that is used to split chlorine molecules into free chlorine atoms. These atoms are also called free radicals and are very reactive. They react with alkane molecules replacing hydrogen atoms. In the first reaction, one chlorine atom displaces one hydrogen atom from the methane molecule, forming chloromethane and hydrogen chloride. In the next step, another chlorine atom displaces another hydrogen from the chloromethane molecule to form dichloromethane and another hydrogen chloride. In the third step, another chlorine atom displaces another hydrogen atom from dichloromethane to form trichloromethane. In the last reaction, another chlorine atom displaces the last hydrogen from trichloromethane to form tetrachloromethane and hydrogen chloride. These products are colorless and the reactions result in decolorization of chlorine gas. Next group of hydrocarbons, alkenes. Alkenes are a group of hydrocarbons which contain at least one double bond between two carbon atoms. They form a homologous series with the general formula CnH2n, where n is an integer and it's not 0 nor 1. Successive members of the series differ by the group CH2. Because the double bond must exist between two carbons, then the simplest alkene contains two carbons. From the general formula, it means the molecular formula will be C2H4. It's called ethene. The open structural formula will be like this or this. Remember, a double bond means 4 shared electrons or 2 pairs. So each carbon has contributed 2 electrons. To complete the valency of 4, each carbon then bonds to 2 hydrogen atoms. The condensed structural formula will be CH2, Alkenes are named from the corresponding alkanes by replacing the suffix "n" in alkanes with "in" for alkenes. So the second alkene with 3 carbons will be called propene. This is its open structural formula, and we can condense that to this. Its molecular formula is C3H6. Next, isomerism in alkenes. Now, alkenes with more than 3 carbon atoms exhibit isomerism. That is the occurrence of 2 or more compounds having the same molecular formula but different structural formula. There are 2 types of isomerism: positional and chain isomerism. Positional isomerism results from shifting of the double bond. Because the double bond exists between 2 carbon atoms, its position is indicated using the lowest carbon in terms of position. Consider this structure. This has 4 carbon atoms, so it's supposed to be a butene. But then, in naming it, we must indicate the position of the double bond. To give the bond the lowest number, we number the carbon chain from left to right. The double bond falls between carbon number 1 and number 2. We therefore give it number 1 because it's lower than 2. The number is indicated between the root name and the suffix "in", separated by a hyphen. So this will be but1-in. If the bond moved between carbon number 2 and 3, then the compound will be called but2-in. If you move the double bond here, it means we now number the carbon chain from right to left to give the double bond the smallest number. The compound is but1-in, which we already have. So but1-in and but2-in are the 2 positional isomers of butene. Chain isomerism, on the other hand, occurs due to the presence of a branch on the continuous chain. Generally, in branched alkenes, the parent chain is the one with the double bond. Naming follows the same rules as alkenes, but the parent name has to have the suffix "in". Consider hexene. The molecular formula is C6H12. First isomer is hex2-in, even though we can still have hex1-in. Suppose this methyl detaches and attaches here. The longest continuous chain will be pent2-in. The methyl group branch is on carbon number 3, so the name is 3-methyl pent2-in. The molecular formula is still C6H12. Other isomers are listed on your screen. Now, when there is more than one double bond, we use the prefix di for 2, tri for 3, and so on. So for example, this structure, the longest chain is hexene but with double bonds on carbon number 2 and number 4. so the name will be hex 2,4-diene. We also have a bromo on carbon number 2, so the complete name is 2-bromo hex 2,4-diene. Laboratory preparation of alkenes. Ethene is prepared in the laboratory by exploiting the dehydrating property of sulfuric acid on ethyl alcohol. Ethyl alcohol is added to a mixture of sand and aluminum sulfate. A few drops of concentrated sulfuric acid are added to the mixture. The flask is heated gently up to 170 degrees Celsius. The ethene gas is liberated and collected by downward displacement of water. Industrially, ethene is prepared by thermal cracking of higher alkenes like kerosene. Sand soaked in kerosene and broken china are heated alternately. The fumes of kerosene get absorbed onto the broken china and they decompose or crack to liberate ethene gas, which is collected by downward displacement of water, being sparingly soluble in water. Ethene is colorless and slightly less dense than air. Chemical properties. Ethene is a highly combustible gas. It burns in air with a sooty luminous flame, producing carbon dioxide and vapor. The sooty flame is due to unsaturation because of the double bond. Addition reactions. Now, we have seen that an alkene is not bonded to the maximum possible number of atoms due to the double bond, so it is said to be unsaturated. Alkanes, however, are saturated, no double bond, and therefore no atom can be added to the molecule. The first type of addition reaction is halogenation, and this is an important test for unsaturation. The orange color of bromine water gets decolorized in the presence of ethene. Since ethene is unsaturated, an addition reaction will occur. The double bond will break and bromine will split into atoms and add across the double bond. The product formed is called a dibromoethane. The same will happen if we used chlorine. It will turn from green-yellow to colorless due to formation of dichloroethane. The next addition reaction is hydrogenation, and this is just a reaction with hydrogen. Ethene reacts with hydrogen in the presence of a catalyst to form ethane. The catalyst used is powdered nickel, and the reaction takes place at temperatures of between 150 and 200 Celsius degrees. This type of reaction is called hydrogenation. A similar reaction is used for hardening plant oils, which are liquids at room temperature, to form solid fats. Such oils contain double bonds in their structure. When hydrogen is added to the double bond, the melting point of the oil is raised, making it a solid at room temperature. Another addition reaction is the reaction with hydrogen halides. Hydrogen halides include hydrogen chloride, hydrogen bromide, and hydrogen iodide. They react with ethene to form alkyl halides. For example, with hydrogen iodide vapor, iodoethane is formed. The reaction takes place rapidly at room temperature. Hydrogen bromide reacts less rapidly with ethane at room temperature to form bromoethane. Hydrogen chloride will only react with ethene when heated in the presence of a catalyst to form chloroethane. Reaction with bromine water. Now, if bromine water is shaken in a gas jar containing ethene, it becomes decolorized. This is because hypobromous acid that is present in bromine water reacts with ethene to form 1-bromoethanol, which is colorless. The reaction is used for distinguishing ethene from gaseous alkanes, which do not react with bromine water. A similar reaction occurs with chlorine water, forming 1-chloroethanol. Reaction with acidified potassium permanganate or Bayer's reagent. Ethene decolorizes the purple color of acidified potassium manganate 7 solution because the manganate 7 ions are reduced to manganate 2 ions. Next, polymerization of ethene. Polymerization is the process by which small molecules link up together to form much larger molecules called polymers. If ethene is heated to a temperature of 200 degrees Celsius at high pressure, the double bonds break and the remaining molecules attach in a series to form a long-chain polymer called polyethene. To write this in equation, we will show this, where n represents a large number of molecules and the square brackets show the repeating units. Here is the molecule chloroethene, which can also undergo polymerization. Here are chloroethene molecules in a row. Double bonds break and the molecules join to form a polymer. In equation, we show that n molecules of chloroethene as the repeating units of the polymer. Polychloroethene is a common polymer commonly called PVC, polyvinyl chloride. It is used in plastic windows and doors, pipes and chairs. Hydration. If a mixture of ethene and steam is heated to a temperature of 300 Celsius degrees at high pressure and passed over a catalyst of phosphoric acid, ethanol is formed. This reaction involves the addition of water to ethene, a process called hydration. The reaction is used for the industrial production of high-purity ethanol. Third and the last group of hydrocarbons, alkynes. Alkynes are a class of hydrocarbons which contain at least one triple bond between two adjacent carbon atoms in the chain. Because of the presence of the triple bond, they are said to be unsaturated, which basically means the carbon atoms are not bonded to the maximum possible number of other atoms, that is 4. The simplest alkyne is ethine, commonly called acetylene. It has the molecular formula C2H2 and the following structural formula. The names of straight chain alkynes are derived from those of the corresponding straight chain alkanes by replacing the suffix "-ane" with "-ine". For example, the one with 3 carbon atoms is propyne, which is derived from propane. With the exception of ethine and propyne, the names of all other alkynes include a number which indicates the position of the triple bond. When indicating the position of the triple bond, the carbon atom occupies the lower position is used. With ethine and propyne, the triple bond can only occupy one position, that is at carbon number 1, as shown by their structural formulae. Therefore, it is not necessary to give a number. Alkynes with only one triple bond comprise a homologous series with the general formula CnH2n-2. Isomerism in alkynes. All alkynes with 4 or more carbon atoms show structural isomerism, that is the occurrence of compounds having the same molecular formula but different structural formula. Position isomerism is shown by the occurrence of two or more alkynes having the same molecular but different positions of the triple bond. For example, the compounds shown on your screen have the same molecular formula, C4H6, but a different location of the triple bond. They are positional isomers of butane. They are named by indicating the position of the triple bond. This is but1-ine and this is but2-ine. Chain isomerism is shown by the occurrence of straight chain and branch chain alkynes with the same molecular formula. For example, the compounds shown on the screen have the same molecular formula, C5H8, but different structural formula. The compound on the left is a straight chain alkyne and the one on the right is a branch chain alkyne. They are isomers of pentyne. The naming of branch chain alkynes follows the same rules as the naming of branch chain alkenes. For example, in this structure, we first determine the longest continuous chain of carbon atoms that has the triple bond between two adjacent carbon atoms. This is the root chain and will give us the root name of the compound. In this case, the longest continuous chain has 4 carbons and the root name is therefore butane. Then we number the carbon atoms in the longest continuous chain, and the numbering should be done in such a way as to give the position of the triple bond the lowest possible number, irrespective of the position of the branch. In this example, the numbering will be done from left to right, giving the position of the triple bond as 1. And therefore, the specific root name is actually but1-ine. Then we identify the side chain or the substituent group attached to the root chain and its position. In this example, the side chain is methyl group attached to carbon number 3. We now name the compound by giving the position and the name of the side chain followed by the root name. In this case, the name of the compound will be 3-methyl but1-ine. Laboratory preparation of alkynes. Ethine is commonly prepared in the laboratory by the action of water on calcium carbide. On a layer of sand, a few pieces of calcium carbide are taken in a conical flask. Water is then added dropwise on the calcium carbide pieces. Calcium carbide reacts with water to produce ethine gas. Being insoluble in water, ethine gas is collected over water. Chemical properties of ethine. Combustion. Ethine steadily burns in air or oxygen to form carbon 4 oxide and water vapor. The flame is smoky and luminous due to the presence of unburnt carbon particles, and this is because of the unsaturation of the compound. Addition reactions. Ethine is a highly reactive gas, and this is because it contains a triple bond and is therefore unsaturated. As a result of this, it can undergo addition reactions similar to those of ethene. When bromine is added to ethine gas, the reddish-brown color is quickly discharged due to formation of tetrabromoethane. hydrogenation. Ethane reacts with hydrogen in the presence of a catalyst to form first ethene and then ethane. The catalyst used is finely grounded nickel, and the reaction takes place at a temperature of between 150 and 200 Celsius degrees. Next, reaction with hydrogen halides. The hydrogen halides include hydrogen chloride, hydrogen bromide, and hydrogen iodide. They add to ethane to form alkyl halides. For example, hydrogen chloride reacts slowly with ethane to form chloroethene, also called vinyl chloride. Vinyl chloride can be polymerized to form polyvinyl chloride, PVC, which is an important industrial product. Ethane decolorizes the purple color of acidified potassium manganate 7 solution.